Hello everyone. In this last video of dynamic programming, we review the probabilistic dynamic programming, and with a brief conclusion, we close this part. Let's review this concept and one example. Probabilistic dynamic programming differs from deterministic dynamic programming that we learned in the previous parts, that the state at the next stage is not completely determined by the state and policy decision at the current stage. As you remember, in deterministic dynamic programming that we had in the stage n, based on the contribution of xn, what happened in a stage n plus 1 was Sn plus 1. But here in probabilistic, necessarily doesn't state totally the current the state of the next stage. Rather, there is a probability distribution for what the next state will be based on a probabilistic probability distribution. We'll see what is the next state. However, this probability distribution still is completely determined by the state and policy decisions at the current stage. Although it was not just a 1 and 1 in stage n and stage n plus 1, but all the stages, probabilities of stage n plus 1 will come based on the distribution of the stage n with one different, of the contribution of these probabilities. That we'll see in our example in the next slides. So, to understand better this explanation, let's see the decision tree figure 11.10 on the next slide. This diagram shows the relation of the probabilistic dynamic programming. So, let S denote the number of possible states at stage n plus 1, and label these states as 1, 2, 3, and S until S. As you see here, for sure, because they are optimal, is Fn plus 1 star of 1, 2, up to S. The system goes to state I, one of these items, with the probability of Pi. Obviously, this I is from 1 to S, with the decision of Xn. Okay, as you remember, before we had this decision and to the stage n plus 1, but now with these probabilities, these items happens. If the system goes to state I, one of these states, Ci is the contribution of stage n to the objective function. So in the real case, in the examples, if we expand this one to include all the possible states and decisions at all the stages, it is sometimes referred to a decision tree. We remember in the previous chapter we had the concept of decision tree, and it summarized everything about this example. To illustrate better this concept, let's review one idea. Suppose that the objective is minimize the expected sum of the contributions from individual stages. In this case, Fn, Sn, and Xn is the minimum expected sum from stage n onward, and state and policy decision and stage n and n are Sn and Xn respectively. Up to here, all the items are like the deterministic part, with one difference that in the next slide we'll see that. So, like the previous form deterministic, as I told you, many items like this one and this one are there. same items that we learned before. The only thing that differs here is this probability. Okay, so Fn of Sn and Xn is the sum of Pi multiplied by Ci plus F star n plus 1 of I, with that this one obviously in this very example is minimization of Fn plus 1 of I and Xn plus 1. In continue, we review one important example of probabilistic dynamic programming to understand better the concept of this item. Let's review an example 6 of our book that is in page 466 of the Hillier and Lieberman, okay, our book. So, the name of the example is Winning in Las Vegas. Let's review this example together and understand it. An enterprising young statistician believes that she has developed a system for winning a popular Las Vegas game. Her colleagues do not believe that her system works, so they have made a large bet with her that if she starts with 3 chips, she will not have at least 5 chips after 3 plays of the game. So she starts with 3 chips, and the form of winning this bet with her colleagues is after 3 rounds of playing, she has at least 5 chips or more than that. This is the condition of winning the bet. Each play of the game involves betting and the desired number of available chips, and then either winning or losing this number of chips. So what is the meaning of that? It means that she can play and bet, and if she wins, for example, if she bets 2 chips, if she wins, she win 2 chips, exactly those 2 chips. So it's 2 more. If she loses exactly the number of chips. In this case, is 2. All the other numbers are the same. So the statistician believes that her system will give her a probability of 2 divided by 3 of winning. Obviously, the probability of losing is 1 divided by 3 or 33%. Assuming the statistician is correct, we now use dynamic programming to determine her optimal policy regarding how many chips to bet at each of the 3 plays of the game. The decision and each play should take into account the results of earlier plays, for sure. And what is the objective? The objective is to maximize the probability of winning her bet with her colleagues. Okay, so she wants to maximize the chance of winning over her colleagues. So what is the key assumption is after finishing the 3rd round of the game, she has more than 5 or exactly 5 chips on her hand. Let's review in the next slides the other concepts. The first step, as always, is formulate the example and understand what are the different concepts in this example. We know that our objective is maximize probability of winning her bet with her colleagues, okay? So, to this end, stage N is nth play of game. We know she has 3 turns, 3 rounds to play, round 1, 2, and 3. Xn is the number of chips to bet at stage N, as we know, is the decision variables. Okay, so she decides how many chips to bit to play. Again, I repeat, based on the example, what she wins, what she bets, she wins. What she bets, she lose. Okay, if she lose, she lose at the same amount. If she wins, is the same amount. And stage n, state Sn is the number of chips in hand to begin stage n. For sure, when she plays round 1, what she has available in round 2 exactly comes from round 1. And with this idea, what she finishes uh, round 2, she enters to round 3. So to this end, Fn of n and xn is the probability of finishing 3 plays with at least 5 chips. Given that the statistician, this girl, starts stage n in the state Sn, makes immediate decision Xn, and make optimal decisions thereafter, for sure. And obviously, she knows that Fn star Sn is maximum of Fn of Sn and Xn. So let's see in our next slide in a diagram what are these formula and what is the mathematical form of the formula. In this game, there are two possible happenings for this statistician, or winning or losing. As we know that the number that she wins or loses is exactly the number that she decides to bet. So to this end, if she loses, the state at the next stage, guys, will be Sn minus Xn. What we have in Sn stage n, okay, minus the decision that we made at this stage, okay, and the probability of finishing with at least 5 chips will then be Fn star, Fn plus 1 star, sorry, of Sn minus Xn. And from the other side, if she wins the next plate instead, she wins exactly the same number. The state will become Sn plus Xn. Okay, so at this state she has 2 and she wins 2. Okay, if she wins these 2, she has 2 more. Okay, so it's 2 plus 2. That is exactly this part. That is 4, for example. So based on the probabilities that we know that she wins with 2 divided by 3 and with the probability of 1 divided by 3 she loses, the Fn, Sn and Xn will be 1 divided by 3 multiplied by the form that she loses that we found here, and 2 divided by 3 multiplied by Fn plus 1 star Sn plus Xn, this part of the winning, where F4 star S4 is defined to be 0 for S4 less than 5 and 1 for S4 greater than 5. We'll see what are the meaning of these items. Thus, there is no direct contribution to the objective function from stage n other than the effect of then being in next state. To this end, and what we see here, this is a probabilistic dynamic programming problem. Let's review the solution of this example to understand it better. In this figure, you see schematically what happens and what is this formula, no? With the stage n, with the possibility, okay, and available Sn, based on the decision Xn we know, with the probability of 33%, she loses. So what she remains for her in stage n plus 1 is Sn minus Xn. And with the probability of 67, she wins. So what she remains is Sn plus Xn. So from one side is F star n plus 1 of Sn minus Xn, and vice versa, the other side of winning is F star n plus 1 Sn plus Xn. Like the other examples of dynamic programming, we start our example from the very last stage, that is n equal to 3. Okay, why? Because we have 3 rounds of playing that are the stages of our game. So pay attention. This is the formula that we found before based on the probabilities of winning or losing. Okay. So we are at the last round. We need to try our chance, okay, and to see how and based on what results the girl is winner. Pay attention, guys. This table is based on the chance of winning. We want to know to how we bet to win, okay? We just want to review this part. So our imagination is that what we bet, we win. So pay attention to these 3 numbers, 0, 1, and 2. We know that the condition and the situation of winning is having at least 5 chips or more than that. Okay? But imagine, and from the other side, before continuing, from the other side, we know if we bet xn and we win that, we win exactly xn. So if I decide to bet 0 or 1 or 2, let's see what happens. If I decide to win 0, to bet 0, sorry, it means that I don't have any on hand. So I don't have anything. If I bet one that I have in hand, okay, and win it, is 1 plus 1, that I have 2. What is the condition? Is having 5 at least. Do I achieve to this point? No. The same, 2. If I bet as a maximum, the 2, okay, the maximum, that is 2, and I win it. So it means that I have 2 and I win 2 more. So 2 plus 2 is 4. So I still don't achieve to this objective, that is 5. So it means that in these 3 forms, there is no possibility to win. The chance of winning is 0. So for sure, with none of the x's, it's possible to win. But let's review the other parts. If I have 3, how many chips do I need to bet with this imagination that we win that to achieve to that to that 0.5? Yes, exactly, is 2, because 3 plus 2, it gives me 5. It means that from 3 of the chips, I need to bet 2 of them and win those 2 to have 3 plus 2, 5. Obviously, if I win more than, if I, sorry, bet more than 2, that in this case is 3, okay, and win that, I will have 6. It's already a winner again, because 6 is greater than 5. But let's review what is the formula for this 2 divided by 3. So we learned that in this case, we are allowed to bet 2 or more. So let's find this 2 divided by 3. So it means that is f3 of s3 and x3 equal to 1 divided by 3 f 4 star of Sn here is 3. Xn is 2 or more. So it means that it can be 2 or 3, but we'll see they are equal. Let's check with 3 minus 2, okay, plus 2 divided by 3 f star 4, okay, multiply by 3 plus 2, okay. As you remember from the previous slides, we had these definitions, no? S4 less than 5, less than 5, yes, exactly. If 4 star, if 4 star, okay, S4 is equal to 0, and if S4 is greater than or equal to 5, if 4 star of S4 is equal to 1. Okay, we know these items. So let's form our formula, this formula that we have in the previous part. That is 1/3 if 4 star of 1 plus 2/3 if 4 star of 5. Okay, so based on the definition that we have here, let's follow. If 4 is S4 here, S4 is 1, is less than 5. So this one is 0. S4 is 5. So F4 star of 5 is 1. So 2/3 multiplied by 1 is this 2/3 that we calculated here. Okay? So let's continue with the other parts. Let me clean this slide to calculate the rest of that. So guys, the same happens in the next slide, okay? In the next item, sorry, that is 4. That is 4, it means that we have 4 in our hand, and we want to know with what form of betting we can win. If I bet one chip that I have on hand and win it, I will have at least 5. And what is the meaning of that? The meaning of that is I'm already a winner. But obviously, if I bet more than 1, that is 2, 3, or 4, okay, it means that I will have more than 5 and I'm already a winner again. Okay, with the same concept that we had previous parts, this 2 divided by 3 can be obtained. Okay, so as an example, when I say, guys, here 1 or more, it means that they give me all of them, 1, 2, 3, or 4, because here I have maximum 4. I have the same result. For example, I will check with 3. Okay, it's that 1/3 if 4 star of Sn is 4 and Xn in this case is 1. Okay, is 3. Sorry, so 4 minus 3 is 1. So 2/3 of F4 star of 3 plus 4 is 7. So based on what we learned before, if S star is less than 5 is 0, and if S star, that is 7 here, is greater than or equal to 5 is 1. So 2/3 is the result of this part. You can check it with the other parts, but all the forms, or 1 or 2 or 3 or 4, you can see that this part is less than 5, that is 0, and this part is greater than or equal to 5, that is 1. So this is the form of this calculation. Let's check the last one, that is greater than or equal to 5. So if I have on hand 5 or more chips, what should I do? If I have 5 or more chips on hand, it means that I already am a winner, okay? And it means that I don't need to bet, or I need to bet in a manner of more than or equal to 5, okay? It means that, for example, if I bet 5, if I bet 0, it means that this part, okay? Because as you see here, less than or equal to S3 minus 5, it should be. So 7 minus 5, if I win that, already I am over 5, I'm a winner. 8 minus 5, I'm over 5, I'm a winner. So this is the result of how to bet when it's more than or greater to 5. So, and to write this formula, to calculate this one, is 1/3 if for star of, for example, for 0, I calculate is 5 minus 0 plus 2/3 f star for of 5 plus 0, okay? So here is f4 star 5, and here is f4 star 5. Both of them is 1. So 1/3 plus 2/3 is equal to 1. So this one is the one that we see in our table. Let's continue with the table n equal to 2 to learn it better. In this slide, we are in stage 2, okay? Again, these are the different possibilities, okay, of having chips after playing one round in n equal to 1, okay? And as you see, guys, these are the probabilities, okay? And these are the different possibilities of make a decision. So, in the case of having 0 on hand, and the only decision is making a decision 0 for this one, because it remains nothing for us. In case of having, okay, 1 as well, always I am a loser, because if it's 1 in hand and I bet it as a maximum, okay, as a maximum, it's 0, okay? So in case of having 2 on hand, that's what I have here, and make a decision 0, 1, and 2, if I check my formula that I have here, I will find these results 0, 4 divided by 9, and 4 divided by 9 here. What is the meaning of that? It means that our S2 here is 2. For example, for this 4 divided by 9, and our x2 is 1. So 1/3 of f3 star of 2 minus 1, that is 1. If you check the slide of the previous part, f star of 1, okay, is 0. Okay, f star of 1, 0, so 0 multiplied by 1 divided by 3 is 0. But this side is 2 divided by 3, f star of 2 plus 1, f star of 3. So f star of 3, f3 star of 3, sorry, if I check in the previous slide, is 2 divided by 3. So 2 divided by 3 multiplied by 2 divided by 3 is 4 divided by 9 here. Or this side, with the same reason, the same part, the first part is 0, and the second part is 2 divided by 3. F star multiplied by what? S2 is 2. X2 is 2, so is 4. F star of 4 of the previous table is 2 divided by 3. So 2 divided by 3 multiplied by 2 divided by 3 is 4 divided by 9. So, like the previous part, what is the maximum of these elements is 4 divided by 9. From what part comes? From betting or 1 or 2 chips, betting 1 or 2 chips. Okay, let's review this part. For example, this 8 divided by 9. What is that? It means that I have 4 on hand and make a decision to bet 1. What happens here? It means that is 1/3 f star 4 minus 1, 3, f star of 3, f3 star of 3 plus 2 divided by 3 f3 star of 5. So f3 star of 5 is 1. Okay, so it's 2/3 this part, and this part is 1 divided by 3 f3 star of 3. 4 minus 1 is 2/3. So 2/3 multiplied by 1/3 is 2 divided by 9 plus 6 divided by 9, that is 8 divided by 9. If you calculate this formula, is really easy obtained. So the other items as well can be calculated from this side. As you see here, guys, these parts, okay, all of them are 2/3. Why? Because 4 minus 2 is 2, 4 minus 3 is 1, and 4 minus 4 is 0. So all of this part is 0 based on the previous slide, and what it happens is this part. So let's check this line. The maximum is 8 divided by 9. That comes from making a decision of betting 1 chip. And this line, all of these items are 1. Okay, all of these items are 1, but I just write this one in this part. Why? Because when I have 5 or more than that, I'm already a winner. Okay, I already a winner. But what happens? I don't bet. I don't bet, because if I bet, okay, nothing happens and nothing changes, because I'm already a winner. And based on what we have, it's f3 star of 5 minus 0 and f3 star of 5 plus 0. These are 1, okay, 1 and 1. So multiply by 1/3 and multiply by 2/3, this part, it gives me 1. Okay, so what is this 1? It comes from, it gives me this one, the maximum of that is dividing, that is deciding to not betting. Okay, that is 0. So we have all these elements and all these elements now. Let's check our last table. Now, in this part, we have the stage n equal to 1. What is the meaning of that? It means that we are in the starting point of this betting game. Okay, so I have 3 available in my hand, so I can make a decision from 0 to 3. And based on this formula that we obtained, calculate it easily. Let's check, for example, this item, how we obtain this one. That is, if 1 of S1 and X1 is equal to 1/3, F2 star of, what is our S1? 3. What is our X1? Is 1. So 3 minus 1 is 2. Plus 2/3 of F2 star, okay, F2 star of 3 plus 1 is 4. So the result is 1/3 F2 star of 2. If I check in my previous table, is 4 divided by 9 plus 2/3 multiplied by F2 star of 4, that is 8 divided by 9. 8 divided by 9. So this part, this total gives me 20 divided by 27. The other parts as well can be calculated easily. If you see here, between 2/3, 20 divided by 27, 2/3, and 2/3, which one is the maximum? 20 divided by 27. And it means that we should make a decision of 1 in this step for our problem. Okay, so this policy gives the statistician a probability of a statistician a probability of 20 divided by 27 of winning her bet with her colleagues. Now, as always, let's check the different steps to find what are the optimal decisions in each of these rounds. That is our next slide. So to find the results, let's review our slides that we obtained in the previous part. As you see here, our decision in the first round is betting 1, okay? So betting 1, if the statistician wins this one, it means that at the second round, she starts with 4 chips, okay? With the 4 chips. And what is the decision of this part? Is betting 1 more. So as you see here, is X2 star is equal to 1. But if she loses, it means that 3 minus 1, 2. What are the sorry, what is the S2 here now? Is 2, 3 minus 1. What are the decisions, 1 or 2? Okay, so let's continue this line, then we follow this line. What is the meaning of this part? X2 is equal to 1. If she wins, okay, it means that 3 plus 1 plus 1 is 5. If she wins, she starts with 5. It means that her decision should be 0. As you see here is 0. But if she loses, this x2 equal to 1 means that is 3. Okay, because here was 3 plus 1, 4. And she loses this one is 3 again. So as you see here, what remains for her in the third round is 3. That is 2 or more. What is more? 3. as you see here, 2 or 3. Let's follow this line. We continued up to this part. In the case of winning of this 1 or 2, okay, if the case of winning this 1 or 2, what is the meaning of that? 3 plus 1, okay, 3, sorry, minus 1 is 2. Winning 1 or 2, that is 2 plus 1 is 3. As you see here, 3 remains for us. For x2 equal to 1, it means that we should make a bet for 2 or more, that is 2 or 3. If x2 is 2, 2 plus 2 is 4. So she should bet, sorry, 1, 2, 3, or 4. Okay? At this part, if she loses this 1 or 2 that she bets in the second part, it means that 3 minus 1, 2. 2 minus 1 or 2 minus 2, it remains for us 0 or 1. 0 or 1 in the third one. So in the both parts, as we discussed before, bet is lost. So this one is the conclusion and the results that you should obtain with a probability of 20 divided by 27, winning the bet here. Let's conclude this chapter in the next slide. So, as a conclusion, it's important to say that dynamic programming is a useful technique for making a sequence of interrelated decisions, as you saw in the different stages that we reviewed. Besides, it requires forming a recursive relationship, okay, and provides great computational saving for very large problems. As we saw based on these tables and the formulas that we obtain, it's easily to solve. It's easily solve the example of this type of problems. And this chapter covers dynamic programming with a finite number of stages, and in the next chapter that in our book is chapter 19, in Markovian decision processes, we cover indefinite stages.